Hello, welcome to session 8 in the series Unlock Circuit Design using ADS. My name is Anurag Nigam, and what I'm going to cover in this session is going to be in continuation to what I covered in session 7, which was a common source amplifier. So let's first sum up what is a common source amplifier, right? So I will have a common source amplifier. Okay, some of the quantities I'm going to sum up so that I can compare them with the common gate amplifier. Okay, so first and foremost is the gain. So in this case the gain was divided by GDS2 plus GDS3. Now this is considering the following circuit. Sorry, this is a PMOS device which forms a current mirror, right? And T1, T2, and then there is a reference current IRAF, and then there is a gain stage here which was a common source, and so input is over here, output is over here, and this is grounded. So in this case EV was that AI was approximately infinity, and RO basically is 1 over GDS2 plus GDS3, and RI is approximately infinity. Okay, so this is our summary for common source amplifier. Then we also look at the advantages and disadvantages. So one was input voltage range is very small. Input voltage range is small, and hence uh, bias bias point bias point okay has to be very precise over time, as well as temperature has to be precise. So that's one thing. Second thing was that there was a Miller capacitance CGD, that was CGD uh, that decides first corner frequency. First corner frequency. Okay, and the very last thing is that you are going to have a output which is 180-degree out of phase with the input. So in a Barkhausen criteria you have already lost 180 degrees, so that was a limitation. So now let's go to the common gate amplifier. Okay, a common gate amplifier is the same topology as a common source amplifier. It's just that instead of applying the input at the gate, I'm going to apply the input at the source, right? So let's put together a common gate amplifier. So under gain stages, I'm going to create a new schematic, and I will call this as a CG. So I have a current mirror load. So if I go here to devices MOS, here, then the eighth row from the top is a NMOS and a PMOS device. So I'm going to work with the PMOS device to start with. Okay, and here I am interested in only displaying what I want to. So in this case my model is called PFAT4, right? and the length of the device I'm going to take as twice the minimum length, which is 260 nanometers. 130 is the minimum, and we have discussed this when we were doing a common source, that length basically is going to decide your output impedance and hence the gain. And so this is 2.5 nanometer, sorry, 2.5 micrometer, and the multiplicity is going to be 20. Okay, so that's the device we have. Okay, now F5 will move the, okay, so now this M is 20. Okay, so multiplicity is 20. Now I'm going to take 1/10 of the device, so I'm just going to copy this and take it 1/10. So there I place it. F2, F5 is to move the text, and there you have it. This is a diode connected transistor, and this is a body terminal because it is sitting its own well, so I can connect it to the source. And then I have got the voltage control current sources, sorry, I have got the frequency domain sources, and there is a DC voltage source which is 2.4, right? Right, and then I have a current reference. Here reference current is 100 microamperes. Okay, so with this out of the way, I am going to put the gain stage there. The gain stage is going to be the NMOS, so I am going to just make a copy of this, and then I will just name this as NMOS. Change the device model to be NFET4. Okay, and only display what I want. So I want to display the model, I want to display the length, I want to display the width per finger, and then number of fingers. Now here the number of fingers is I'm going to keep as 8. Okay, and then I have to flip this source at the bottom, and I have to just move the text to the right so I have a place to work with. So here you go. Okay, so now in this case, roughly the voltage which we found at the gate, DC voltage, was 0.612 from previous session. That's V overdrive plus VT roughly, right? So what I'm going to do is I'm going to place two sources here. One will be called VG, right, and the other one will be called VI. So this is a DC source. Now this VG will decide what is the quiescent current for the input, right? So VG, so the quiescent voltage would be VG minus V overdrive minus VT. So that will be the quiescent voltage. And if it is 0.612, so I'm going to say 0.71. Okay, so or 0.75. So I have a 30 millivolt swing, for example, on the input. So 15 millivolt is on the input side, on the lower side. So I would have the quiescent current at least 15 volts, at least 15 millivolts above. So it was 0.612, but let's say I'm going to do 0.71. Okay, so let's set that. So if you take a variable, okay, so one variable is VG. VG is, I'm going to set it 0.71. Okay, 0.71, and then I have got VI, which I'm going to sweep. So I'm going to start with 0.115, Okay, and then I am going to put here the include file, and I am also going to put here what you call sweep. So I'll go to simulation DC, and that's the DC simulation controller. Here I'm going to see VI, okay, from 0 to 2.4 volts, that is up to the supply voltage, and I want to look at the static characteristics of the amplifier. Okay, so as to find the bias point. That's done. So all set, other than I have to just name this one. I have to just name this one as VO. So I think I'm all set. Let me just display this. So see variable start stop step. Say OK, and I'm going to hit simulate. So if you remember, with this sizing, the gain for common source was around 29.6 dB, and we are going to get something similar here. So let me plot output. Okay, let me just check. 260 nano, 260 nano, 260 nano, 2.5 micro, 28. Okay, so this one would be wrong. So this one was around 2. Okay, so now I'm forcing current, which is going to be 1 milliamp. Server error, stream removed. Let me see what has happened here. Doesn't make sense to me. Sometimes. So what's the point? Okay, yeah. So now you see that there is a complete swing. Now, okay, so now this is going to be swing. Now, if you remember, common source had a negative gain. Now this one has a positive gain, or common source has a 180-degree out of phase between output and input. Now here it is going to be in phase. So we are all set. Only thing I need to figure out is where is the quiescent, input quiescent. So it is going to be around roughly around, let's say 1.22 or 0.98, 97 or 98, 97 or 98. So VI is going to be 0.098, 098. So that's my quiescent voltage. Okay, once I have done this, just let me get this out of the way. Okay, sorry about the interruption. Okay, let's go ahead. So now we are all set. We have seen this. Now the issue here, come on. So I don't know why it's saying that. Okay, so the issue here is the upper limit swing is VDD minus V overdrive, but the lower point in the swing is decided by VG minus VT minus V overdrive. So if I was to increase up VG, then this lower part of the swing is going to move up. So for example, let's say I put a tune on this VG. Okay, so this is a tune on the VG, and this is my output. So you will see that if I change VG, I can basically move the point to the right. So let's go up to 1.3 maybe. So I can move the point to the right, but if you see the net swing which is over here, right? So the net swing is, let's say, from here to, let's say, from here. So this is the net swing, okay, when input is VG is 1.3. Now if I reduce VG, this swing is going to increase, if you see, right? So if I leave it at 0.7, okay, you are going to get the entire swing, right? 0.71, let's say. So you understand that now I have a control over the drift. So let's say VT has a drift, and my input signal has been adjusted to certain bias. Now I can adjust VG to compensate for that drift. So this is an additional control which I have got going to common gate. Okay, so you understood that DC wise, that's the control. Now let's see what happened to the AC, right? So what I can do is I can just say copy cell, and here I can save it as AC, right? Okay, so I have that over here. So let me just close these. Okay, so once I have closed this, let's open this one. Now instead of this, I am going to place here AC simulation and AC source. So I will go to sources, frequency domain, VAC here, and everything is fine. Input is 1 volt, so output would be the gain, and DC voltage I'm going to keep as VI, right? So this is what I have determined from the static response, right? And I'm going to make this visible. So that's my input, right? And then I'm going to do AC simulations, simulation AC, and I will go from 1 Hertz to 10 gigahertz, a log sweep with 80 points per decade, and I am going to just display decade, points per decade here. So this is going to be my AC sweep, right? So I'm going to hit simulate, and then I'm going to plot the gain. Okay, so that's the gain. So let me put a log scale on x-axis. So that's the gain. Okay, so if I put a marker, you'll find that the gain is the same as the gain for a common source. Nothing has changed. It's only that you have applied the input at the source, not at the gate. That's the only thing you have made, thing you have changed. Next is, let's look at the phase. So if you remember, the phase was starting with 180, but now the phase starts with 0. So because the phase starts with 0, I haven't lost that 180 degrees in the Barkhausen criteria, right? Second thing to notice is that it's 3 dB, what you call 3 dB corner is around 118 or 120 megahertz, which is going to be much higher than that for a common source, because common source has a Miller capacitance, which when referred to the input is gain times of that CGD. So that sets the first corner. Now in this case, that capacitance is not there, right? Because the capacitance is between drain and body, and drain and body. So body here is connected to, okay, body should be connected to ground, right? Okay, so in case body is connected to ground, that capacitance doesn't exist, right? So let me just do one thing. Let's connect this body to ground. Okay, so when I connect the body to ground, what's going to happen is the Miller capacitance would be 0. The CDB will be to the drain and the body is grounded. Okay, so roughly same point. Okay, so that's the advantage. Now let's just do a small signal model for this one. Okay, so I'm going to, for low frequency, I'm going to ignore all the capacitances. So what I'm going to be left with is going to be the following. Okay, so I would have this side grounded, correct, and I would have this side as the input, and I would have this as the source, and I would have GM which is inverted. So I would have here, let's say RS, and this is going to be V in, and this is going to be VI. So plus minus, so the direction is reversed. So I am going to have GM this way, and then because it's a source is basically at a higher potential DC wise, right? So I'm going to have a body effect. So I'm going to have GM3 plus GMB3, right? And then I'm going to have GDS3, and then if you see, the capacitance will come to ground because CDB is B is ground, so that capacitances are anyways ignored in low frequency model. So I have here GDS2, and then I have got GL. So this is drain, this is gate, and this is your source. Okay, so this is the small signal model which I'm going to use for analysis. Okay, so at the output node, okay, where the voltage is going to be VO, okay, I'm going to write the equation, Kirchhoff's current law. VO times of conductances connected to it, GDS2, GDS3 plus GL. So these are the conductances connected to VO, minus VI times of, so whatever is the adjoining node and in between conductance, GDS3. Okay, and then count for all the sources. Current flowing in are going to be negative, so minus GM3 plus GMB3 times of VI, and then the current. Okay, so this is going to be the current. So let me consider one more current. Let's say this current flowing in is IN. Okay, so now should be equal to the 0. So that's the equation. That means that VO over VI is equal to GM3 plus GMB3 plus GDS3 divided by GDS2 plus GDS3 plus GL. Okay, so now if you look at this one, if I assume that RL is equal to infinity, that is same as saying GL equal to 0, and if I assume GM3 to be much larger than GMB3 plus GDS3, so when this condition happens, this would be approximately equal to GM3 divided by GDS2 plus GDS3. Okay, so that will be AV. Okay, so the AV for common gate is same as the AV for common source, only that there is a negative sign, or there is no 180-degree phase shift between input and output. So that's very simple. Now let us look at RI, right? Sorry, let's look at the Kirchhoff's current law at the input node, or VI. So for VI, all the conductances connected to this are GDS3, right? And then the adjoining node VO is minus GDS3, right? And then account for the currents. So the currents in this case flowing out are positive, right? So they are going to be VI GM3 plus GMB3. Okay, and then there is a current I in which is flowing in, which is negative. This should be equal to 0. Now rearranging the terms, I am okay, and using this equation. So let's collect the terms. VI times of GM3 plus GMB3 plus GDS3. Now VO I can write as VI times of this. Okay, so VO is VI times of that. So I'm going to write here VI. So this is going to be VI times of GM3 plus GMB3 plus GDS3 divided by GDS2 plus GDS3 plus GL times of GDS3 is equal to IN. Okay, so now I'm going to collect the terms of IN by VI. So I have this GM3 plus GMB3 as common plus GDS3 is common, and this will be 1 minus GDS3 divided by GDS2 plus GDS3 plus GL. Okay, so now if I was to solve this side, I am going to be left with, so I'm going to be left with 1 over, okay, so I'm just going to simplify this. I'm going to be left with 1 plus GDS3 divided by GDS2 plus GL. Okay, so that will be equal to IN by VI, which is equal to YI. So that is the input conductance. So now if I was to say that RL tends to infinity, GL is 0, and if I substitute that over here, this factor would become 2, right? So I'll be left with, so if I consider another case, another consideration, GM3 is much larger than GMB3 plus GDS3. So what I'm left with is GM3 divided by 2 is equal to YI. Okay, so the input conductance is GM3 by 2. Okay, so now let us consider what is VO by VIN, which is going to be AV. Okay, of course this is an approximation, right? But still, let's put there the exact value. The exact value would be GM3 plus GMB3 plus GDS3 divided by GDS2 plus GDS3 plus GL times of, okay, so now to find that, one more thing is there. At the input I have got, okay, at the input I can say GS times of voltage across it, which is V in minus VI, will be equal to the current I in. So I will be left with V in by VI is equal to GS by GS plus Y in. Okay, so if I was to multiply this term with that term, divide by that term, just 1 second. So let me just solve this. Maybe I have done some mistake here. Okay, so now V in by VI, I in by VI is YI. So YI will be equal to V in by VI minus 1, and then you have a GS here. So this 1 would come as a GS over here and then divided by GS. So I was doing a mistake here. Okay, so then this term is equal to that, right? So I'm going to divide this by that. So I'm going to divide this by that. So I'm going to have VO by VIN. So I'm going to have VO by VIN is equal to this times of this. Okay, so this is my exact value of voltage gain, but approximate value is same as that of a common source amplifier. Now what about the input impedance? So okay, so AV is clear. So let's look at the input impedance. Ri or Rin is going to be equal to Rs plus 1 over Yi, right? So if I assume Rs equal to 0, then this would be equal to, so if I say Rs equal to 0, 1 over Yi, and this Yi, 1 over Yi simplifies to 2 over Gm3. Okay, so this is my input impedance. Now notice that the input impedance for common source is close to infinity. So when you design RF blocks, it's difficult to match the input to a high impedance. Okay, so now here my input impedance is under the control of Gm3. So 2 over Gm3 is my input impedance, which is much lower than that of a common source. So it's easier to match a common gate amplifier for RF requirements, right? So that's one conclusion. Next is AI is approximately equal to 1 uh, because the drain current is same as the source current. So this has to be, because nothing flows into the gate. So we have that. Now the question comes is, what is the output impedance? So to find the output impedance, I am going to take this circuit. So let's just take this circuit. Okay, copy it and then go to the end of it and say paste it. Okay, so after pasting it, I'm going to remove some stuff. So let me have a bigger eraser to remove this. Okay, so now what I'm going to do is I'm going to short all other small signal sources. So this input will go off. So this would be connected to ground here, right? And then the current direction I have to take is negative, right? So this is the direction of current, and then you have Vi is equal to, so let's say I break the circuit over here. So I have broken the circuit over here, and let's place it to the side. So let's place it to the side here like this. Okay, so that's there. What I'm going to do is I'm going to look inwards this way. Okay, so I'm going to connect here Vx, right, and then I have a flow of Ix. So Vx by Ix is Ro. So let's say if this is Ix, then this should be Ix, right? Because the current doesn't flow into the gate, so this has to be Ix. So Vi will be equal to Rs times of Ix, right? So let's write down the Kirchhoff's current law at the output node. So at output node, Vx times of GDS3, okay, minus Vi times of GDS3, right? And then at this node the current is flowing in, so they are also minus Vi times of GM3 plus GMB3. Okay, and then there is a current Ix which is flowing out. So Okay, fine. So at the output node only this is there, and then there is a IX current which is flowing in, so it has to be negative and 0. So now let us collect the terms of Vi. So I will have Vx GDS3 minus of Vi is substituted by this Ix times of, okay, so Ix is common here, 1 plus, and then you have Rs times of Gm3 plus Gmb3 plus GDS3, right, is equal to 0. Now I can move this term to the right hand side, so I'll be left with this thing equal to this. So I have Vx by Ix, and I'll multiply both sides with RDS3 times of 1 plus Rs Gm3 plus Gmb3 plus GDS3, right. So this is going to be my output impedance RO dash. So this is equal to RO dash. The RO would be equal to 1 over GDS2 plus GL. So now I'm bringing into this equation, these two terms, right, plus 1 over this thing, which is going to be RDS3 times of 1 plus Rs times of Gm3 plus Gmb3 plus GDS3. Okay, so now if I say RDS3 into Gm3, right, that would be the gain. So gain, okay, so over here, okay, so let's move this to the top, so this will become GDS3. Okay, so now what's going to happen is this term will tend to 0, because, so this is Rs, because the gain times of Rs is going to be a very large number, so that term would disappear. Okay, but another thing is, if Rs equal to 0 and GL equal to 0, then I would come to the same number. So I would come to the same number, 1 over GDS2 plus GDS3. So this is under a condition Rs equal to 0 and GL equal to 0. So in this case RO is same as that for a common source. Now with this said, we know now that what are the advantages of a common gate amplifier. Okay, so now let's look at common drain amplifier. Okay, common drain amplifier. Perhaps this is the only amplifier which has a very high input voltage range. If you look at here also, so if you look at so if you look at this one also, the input voltage range is the same as that for a common source, right? So we haven't changed a lot of things going to common gate, but let's see what happens with the common drain. Okay, so in case of common drain, I am going to just modify the circuit and make it a common drain. Okay, so let's look at a common drain amplifier. Okay, so I'm going to copy this file, common gate, and I will make this as a common drain. Okay, let me make sure you are recording it. Yes. Okay, so let's make this a common drain. Okay, so in common drain, what happens is I am going to just delete this one, and delete this one, and I am also going to, so I'm going to delete this. Okay, so let's just keep this aside for now. Let's take this part, so even keep this aside. Let's take this plot and flip it out. Okay, so to flip it, that's there. That's a flip, and this is the current flowing in. And these are NMOS devices. So that's NMOS, and that's NMOS. And what's going to change in this case is this is NFET4, and this one is also NFET4. Okay, and I'm going to display what I want to. So I'm going to clear all. I'm going to just display the model name, the length, the width, and the multiplicity. Okay, and same I'm going to do for this device. Clear all. The model name, the length, the width, and the multiplicity. So still there is a 1:10 ratio. That's one over here, and this part is grounded. Okay, so now I'm going to have the same device, which I'm going to repeat at the top. Okay, so let's see what has happened. So in this case, the input is over here. So this input is over here. And this we don't need. Okay, so the input is over here, right? And then the drain is at a DC ground, DC, which is a small signal ground. So drain is common between VI and VO. So this is a common drain. It is also known as source follower. And what's going to happen is the VO is bootstrapped to VI, and VO is VI minus V overdrive minus VT, right? So if I have a signal on signal over here on the gate, the signal at the drain is going to be same. It's just that it will be DC shifted. So that's why it is also called a level shifter, right, or a source follower. Another thing to know is that this one has got complex poles. Now if you give a step input, so this one has complex poles. So if you give this source follower, sorry, so okay, so if I was to give this a step input, so let's say that's my step input, then it's going to behave this way and it's going to ring and settle down. So this basically depends on what is my, just one second. Okay, so if I was to avoid this ringing, I would have to do a loading of the output with the RC. Okay, so that R is going to give you enough damping. So you have to make this, let's say if you make R to be very small, then the damping would be more, and it will be critically damped, but it will take more time to settle. So settling time would be more. But if you increase R, so that means that you are damping it less. In that case, there would be the overshoot, which will be large. So this is like a second order system, it will behave, right? So I'm not going to go into the details of this, but let's say if I was to do this static characteristics, I'm sweeping VI from 0 to 2.4 volts and VO is over here, and this is my circuit. So I'm going to say simulate, and if I plot output voltage versus input voltage, that's what it's going to do. So at overdrive, okay, at VI is equal to V overdrive, this the top device is going to turn on, and after that the slope is going to be the gain, which would be close to 1. So the gain is 1, right? So basically, yeah, so that's the gain will be close to 1. Okay, so now this one has very high input voltage range, because no matter what you do over here, okay, the output is just going to follow it, right? So that's there. So let's just see what is the gain, right? So let's just copy, maybe, or I can draw it if I want, but let me look at this one. Okay, so I'm gonna copy this one and modify it. Okay, so I'm gonna copy this one, copy, and then I'm gonna paste it over here. Okay, so over here let me remove some things. Sorry. Okay, now one thing more to notice here is this is common drain, so this is ground, and you have this as output. So here again, okay, so instead of RS, let me just remove this also. Okay, so you are going to have GDS2, and then you are going to have GL, and this is VO, and then sorry, okay, so this is going to be VO, so this node is going to be VO, this is the output node, right? And this node is going to be VI, right? And then let's reverse the direction of this. So let's reverse the direction of this. So VI minus VO is supplied to the input, right? So now let's write the equation at the output node. Okay, so we have VO times of GDS2 plus GDS3 plus GL. Okay, so this is there, and then you have the current flowing in minus GM3 plus GMB3 times of VI minus VO is equal to 0. So what I'm going to have is VO times of GDS2 plus GDS3 plus GL plus GM3 plus GMB3 minus VI times of GM3 plus GMB3 is equal to 0. So let's put this like this. So VO over VI. Okay, so let's assume, okay, so let's assume that GL is going to be equal to 0, right? So then I'm left with GM3 plus GMB3 divided by GDS2 plus GDS3 plus GM3 plus GMB3. Now if I assume GM3, sorry, so if I assume GM3 plus GMB3 is much larger than GDS2 plus GDS3, which means that the output impedance of the transistors is high. In that case, this would be approximately equal to 1. So the current gain for a common drain would be 1. What about, sorry, the voltage gain? And the current gain is going to be approximately infinity. The input resistance will be approximately infinity. What about the output resistance? For output resistance, I'll take the same. So let's just take the same and then make a modification to this. So I'm going to say copy, and I'm going to paste it over here, the diagram. Control V. Okay, so now here I'm going to short all the sources other than the output where I'm going to put Vx. So this is not there, so I am going to have this one grounded. So all I have is a VO at the input, and this would be reversed, so this would be reversed, so this would be reversed towards up. Okay, so I would have the output node, and then I would here I would do the following. Okay, on the output I'm going to connect a Vx and force a current Ix, right? So I have a Vx forcing a current Ix into this. Okay, so I need to write this equation at the output node. So I have Vx times of GDS2 plus GDS3 plus GL. Okay, and then the current which is flowing out of the node is positive, so that will be GM3 plus GMB3 times of Vx. Okay, and then minus the current flowing in is equal to 0, or I have Vx over Ix, which is going to be RO, which will be equal to 1 over GM3 plus GMB3 plus GDS2 plus GDS3 plus GL. Now that means that the output impedance, output resistance is going to be very low. Okay, if these numbers are large, the output resistance can be low. Okay, so this basically completes the treatment for a common drain. So I'm going to stop here for now, right? And then I will go into differential gain stages in the next session. Okay, thanks a lot.